Hello, good evening learners. Today we will discuss about a week 8 assignment of last semester uh, and we also discussed about the concept uh, taught in last week lectures. Okay, so we should start now. It is 6:02. So this is the last class of week 8 and if you have any question you can write me. I'm sharing my email ID in uh, message chat box. Just a minute, because whenever you will able to see this class, you can contact me. If you have any doubt or any question regarding your exam or assignment, okay, you can write me on the said email. Okay, so we should start now. Week 8 assignment, question number 1. For a Newtonian polymer melt. Okay, so the shear stress is proportional to what? Shear strain. Okay, shear stress is proportional to shear strain. shear strain rate, okay, yield strain no, and maximum strain no. Okay, so for Newtonian, because it is Newtonian polymer melt, the shear stress will be proportional to its shear strain rate. Okay, just a minute, somebody. Okay, so uh, Devendra, are you able to hear me clearly? Devendra, am I audible? Hello, am I audible to you? Okay, please text me if I am not audible, or if you have any doubt, you please text me. Okay, I think I am audible and my screen is visible to you. If you are not, then please write. Am I audible to you, students? Kirtiva and Devendran, am I audible to you?
Yeah, sir.
Okay, okay. Yeah, if I think you are able to see my screen also, means my PPT which I am sharing.
Yeah,
If
sir.
okay, let me in all.
Sir, I have a question, sir.
Yes,
Sir, actually, if we cool faster, we get amorphous, right, sir?
sorry.
Sir, if we cool the polymer, sir,
Ha
we get amorphous, right? They don't have time to orient, so
ha.
they'll
Ha.
not form crystal. They
Yes,
form
yes,
amorphous. And
yes.
the thing is, the TG is higher than slow cooling.
TG is higher in slow cooling. Yes.
No, sir, higher than slow cooling, sir. Like if we get fast cooling, the TG will be high, no, sir.
If you are fast cooling, then obviously yes, it will be amorphous. So TG will be high.
Yeah, sir.
You are saying that TG is high for smart fast cooling.
Sir, actually, if we get amorphous, we
Yes,
require less energy to melt, right?
yes.
Like to form.
Means the
So
question.
the TG should be low, right?
I understood your question. You are asking that if I am cooling fast, if cooling rate is very high, then it should be amorphous.
Yeah.
So its TG
Yeah,
should
sir.
be less compared to
Yeah, sir.
semi-crystalline or crystalline material, right?
Yeah, sir.
So
Yeah, sir.
yes,
Right.
yes. Okay, so I will answer you this question. Okay.
Okay.
Yeah, I have shared my email ID. See, so where you get this information that TG is high, please write me. I will
Okay.
share detailed answer. Okay, because
Sure, sir.
because according to me also, it TG should be less because it is
Okay, sir.
amorphous,
Fine.
so TG should be less. So what is the phenomena behind
Okay.
it? We will discuss. Okay, please
Okay,
write
sir.
me. Did you get my email ID?
Sir, is it in text? Sir, could
Yeah,
you please
it is
share it
texted.
in text box, sir?
Ha, I
Sure,
have
sir.
already said, but I will say once more. Just a minute.
Okay, sir.
Okay. Are you able to see now?
Yeah, sir. Thank you, sir.
Ha ha.
Yeah,
Please,
sir. I got it.
yes, please write me so I can revert you. Okay. Otherwise, I will forget and all things will be
Oh,
happen.
okay,
So
sir.
just write
Sir,
me
and
after this class. So I will revert you till Monday evening surely. Okay.
okay, sir.
Ha.
Sir, then one more doubt, sir.
Yes.
Sir, in a Florifork equation, I got an answer like 1 divided by 0.0031, sir.
Hmm.
Sir, should we definitely take 4 digits, sir? Like for TG, Florifork's equation.
Four digit. Who asked you to take four digit?
Sir,
Where? Huh.
actually, the value is like 1 divided by 0.003283
Huh.
something, sir.
Yes. Yes.
So the numerical value other than a non-zero should be like 4 digits should we take or
Miss,
two
can you?
digit is enough.
Yes. Can you repeat the value? What is the value?
Sir, I'm just saying as an example, sir.
Huh.
Like 1 divided by 0.003284, sir.
0032 like that. Are you able to see my screen? I'm writing here. So
Yeah, sir.
one divided by point 0.003 like that.
3, 8,
Huh.
something, sir.
Okay, whatever. Okay. So what you're asking?
So if we need to, I'm asking like we should take 4 digits like numerical value after 3, 8, 2, 4 something is there means should we take that also into
No, no,
consideration?
no, no. I think it will not make any sense. Okay.
Sir, actually, assignment last assignment, sir, I
Hmm.
took just 2 digits like 3, 8 something I took, sir.
Hmm.
I got answer like 39.5, sir.
Okay.
But the range is from 40.1 to some 41, sir. So I got like point 0.5 difference, sir.
So, Miss, so this is the weight percentage, na? Sorry, this is the what is for Fox equation 1 T upon W uh, upon T1 like
Yeah,
that,
sir.
na?
1 by Tg is equal to
W
W1 by T1 plus W2 by T2.
just like that. Okay. So this is the
Okay.
temperature. This one will be okay. So finally you got this value after solving like that. Okay. TG.
Okay, sir.
Hi. Okay. So yeah, if you solve there, just then what will happen? So it will be 38. Okay. And if it's
Okay.
38.22, so it should be considered. I think means yeah, if okay, so it will be
Okay,
38.2.
sir.
Otherwise, it will be 38.2. Means in your case, am I right?
Okay, sir. Yeah,
Okay,
sir.
so it will not make much difference. Okay, but
Okay.
if you want to clarify, so you can write to instructor that sir I did in this way.
Yeah, sir.
So otherwise it is correct, but
Okay, sir.
there is some limitations of means answer na.
Okay,
So that's
sir.
why otherwise your answer
Yeah,
is
sir.
right. Your answer is right means we can say, but
Okay, sir.
I think sir provide only. Uh, less tolerance. That's why your answer is
Okay, sir.
means beyond the limit. That's why it is making
Okay,
not.
sir. I
Huh.
too will recheck my answer then, sir.
Yes, yes, yes. Okay, so it will not
Okay, sir.
make
Thank you, sir.
very much difference. Okay, because it's 38 and
Okay, sir.
38.2. So I think it is not
Yeah.
make sense. Okay. Yes.
Okay, sir. Fine.
Huh.
Thank you.
Okay, just a minute. Just a minute. Okay, so question first I have already explained, but now many students joined, so I just read it fast. Okay, again, for a, Newtonian polymer melt, the shear stress is proportional to. Okay, so it is very simple question. I think all you all know about the answer. Shear stress. So shear stress is proportional to shear strain rate for the Newtonian flow melt. Okay, we will discuss it. Shear rate. See, this is the question. Okay, it is for non-Newtonian flow. There are many non-Newtonian flows are represented here, along with Newtonian flow. Okay, so here you can see Newtonian flow. So shear stress is proportional to shear rate. Okay, so this is the graph for Newtonian flow. Okay, so by explaining this graph, we can say that for a Newtonian flow, shear stress is proportional to shear rate. Okay, so this is the right answer of this question. Then question number two, identify the behavior of plastic sample represented in the following plot. Okay, so this is the plot. So here, this is the plot in between shear stress and shear rate. The same graph which I explained previously. Okay, so here what is happening? See, up to some limit it is proportional. Then it is by increasing shear rate, the shear stress is decreasing. See, up to here it is proportional, linearly proportional like that. After that, when you increase shear rate very high, the shear stress is decreasing. Means what is happening here? Means it is becoming shear stress is decreasing, means you can say it is becoming less viscous. Okay, so it is becoming less viscous. So these type of materials are very useful, because when it will become means if at higher shear rate, if it is becoming a viscous solution, then it will be easy to processing. Okay, so for elastic too, if it is becoming viscous, okay, and if you increase more shear rate, then it will become less viscous. Okay, so means you can say viscosity is decreasing if by increasing shear rate. So it will be help in polymer processing. Okay, so this type of phenomena is known as shear thinning. Thinning means your uh, polymer or whatever your feed material for processing is becoming thinning, means it is this viscosity is decreasing by increasing shear rate. Okay, so this type of phenomena is known as shear thinning. Okay, so it is Newtonian flow. No, we have already discussed in first question that it is straight. Okay, so this is the wrong answer. Then shear thickening, sorry, shear thickening, so not thickening. Okay, it is thinning, so it is not right. And Big Bang plastic is also not right. We will discuss what is the Big Bang plastic, but it is not here. So pseudoplastic, shear thinning is also known as a pseudoplastic. Okay, or we can say shear thinning phenomena is happening in pseudoplastic. So this graph is for pseudoplastic. Okay, so B is right answer. B is right answer for this question. Okay, we can see here for the pseudoplastic, initially it is like that. Okay, after that, if you increasing shear rate, shear stress is decreasing. Okay, so it's this phenomena is known as shear thinning. Okay, it is also this and this type of material is known as pseudoplastic. Okay,
So what is plastic, sir?
sorry.
Cash on plastic, sir. Like, what is mean by that, sir?
See, Cason plastic means it has some. If you start shear, okay, shear rate is very low. Then also it has some shear stress at initial point also. Okay, it is like pseudoplastic only, but it has shear stress initially when you start just shear. Okay, see, it is this is the you can say inherent shear stress, na? Shear rate is very low. You can say
Yes.
about zero, but also it has shear stress. So this type of material is known as a caisson plastic. Okay.
Okay, sir.
Then question number 3. The optical property that relates to the reduction of resolution. Okay, reduction of resolution. Okay, so it is simply resolution means you are seeing something by using this media. Okay, optical property of something. Okay, means some polymer you are using for and you are going to resolute something. Okay, you are seeing some image. Okay, and this is used as a lens, we can say. Okay, the lens is made by some type of polymer. Okay, so it is reducing the resolution or reduction in resolution. So this property is known as a clarity, we have already discussed, but here we will discuss this all property in detail. So it will be more clear what is haze, glows, by reference, okay, and clarity. So one by one we will discuss this property. Okay, so answer is D. We know that clarity is the ability. Clarity is the ability to sample to transit the fine detail of an object. Okay, so here the material is using as okay, for fabrication lens, and then you are means suppose this is the object, so you are seeing this object from here. Okay, so you are seeing object from here, and how this material can give you information. Okay, so it is measured as a clarity. So uh, clarity is the ability of sample to transmit the fine detail of an object viewed through it. Okay, so it is using as a medium. It relate the reduction in resolution. Okay, so because polymer is not 100% transparent, we can say. Okay, that's why it makes some reduction in the resolution of your object. Okay, so the measurement of this property is known as a clarity. Okay, so we will discuss a little bit. So, okay, someone is waiting room, I think. Just okay. So I think it is clear. Okay, so what is the haze? Haze, we know that haze is something means not looking clear like that. Okay, in our general dictionary. So the percentage of transmitted light which is passing through the specimen deviate from the incident beam by forward scattering. Okay, it is deviating. Okay, and how why it is deviating? So incident beam is deviating due to forward scattering. Okay, and we measure more than 2.5%. If deviation is more than 2.5%, so the amount of this light flux is being measured. Okay, so it is characteristic of loss of contrast that result when object are viewing through scattering medium. Okay, after passing from scattering medium, how much contrast is lost? So this is the property we are going to measure by this haze caused by both surface and bulk scattering, obviously. Okay, and surface scattering can be minimized by wetting surface with a liquid or similar refractive index. Okay, if you are using this type of liquid, then surface scattering can be minimized. Okay, then clarity. So clarity is ability of sample to transmit the fine detail of object viewed through it. Okay, so you have some object, and how much you are able to see the fine detail of your object. So it is this property is measured as clarity. It relates to reduction in resolution. Okay, so if clarity is high, then if resolution is high, then clarity will be high, like that. It is strongly related to the angular distribution of the scattered intensity. Okay, related to angular distribution of the scattered intensity. Okay, how much scattered, it is only scattered intensity, but angular distribution. Okay, how much it is distributing and how which angle. Then maximum clarity is achieved by minimizing the size of scattering center. It is also affected by distance between the object viewed and sample. Okay, same as we are using in what say magnifying glass. Okay, or microscope. So it is also depend on distance between object and the sample. Clarity is negatively affected by light absorption and scattering. Okay, if either it is absorption or scattering, then clarity will be decreased. Okay, so this is about all about clarity. Okay, what is the reflection? Reflection we you all know. Okay, reflections are simply because we all are very much aware about the glass which we are using for domestic purpose. So and we also know reflection. Okay, so how light is reflecting due to smooth surface, light is reflecting. Okay, and this phenomena is very known, and this gloss is also very known term, but here it is a little bit different. Okay, so I am reading the last sentence why because it is the most important I think. Gloss is the ratio of reflective of the sample to the reflecting of the standard. Okay, so standard we are measuring reflection of the standard. Okay, so what is the standard here? The typical standard for gloss is optically flat. Optically flat means concave and convex we have discussed now this type of glass. So here we are using only optically flat black glass. Okay, so it is black glass. So obviously we know that black is a good absorber of radiation, so it will be absorbed. Okay, now whatever your material, so you are measuring in respect of the standard. Okay, how much amount of incident rays is scattered by this sample. Okay, so by measuring this standard, by comparing your sample with the standard, you will able to measure the gloss of your sample. Okay, so finally I am reading back that gloss is the ratio of the reflectivity of the sample to the reflectivity of the standard. Okay, so you are comparing with you are comparing your sample reflectivity with your standard. Okay, so the okay it is discussed. Reflection is already you know. Okay, so reflectivity is the defined as the ratio of intensity of reflected to incident light. Okay, so I0 is incident and IR is the reflected light. Sorry, reflected light. So this ratio is known as reflection, and you all know that gloss related to reduction in intensity of the light scattered. Okay, so if your surface is not even, okay, if surface is not even, then obviously the scattering will be in various direction. Okay, like that. So it will be in various direction. So its gloss will be decreased. Okay, so that's why we are using plate and black glass. Okay, see. So otherwise it will be decreased. So this is all about the reflection and gloss. I think you understood. If you have any doubt, you can ask. One more term is here. This is by refrigerance. Just a bit. So by refrigerance means it is depend on the orientation of your sample. Okay, if you are measuring light from now from here to here or here to here, it will give different value. Okay, so the material is same. Okay, but it is giving different value. So why it is giving different value? Due to its orientation or chemical structure. Okay, so what is the by refrigerance? Optical phenomena in which a sample exhibit different refractive indices for plane polarized light. Okay, so if you are measuring Rx from this side or Rx from this side, the value will be different. Okay, so you can say Rx not equal to Rx dash. Okay, because you are measuring from the different angle. So optical phenomena in which sample exhibit different refractive indices for plane polarized light in two perpendicular direction. Okay, so this direction are perpendicular. Okay, so it is giving different value. In case of polymer, crystalline phase are by refrigerants. Okay, so crystalline phase, if there is crystalline phase, then it will give different refractive indices. So molecular level we can understand. Okay, so this is the one chain. Okay, suppose it is oriented like that. Okay, so if light is passing like that and light is passing like that, so it will give us a little bit different value. Similarly, by molecular level, you can say this direction has high polarity. Okay, polarizability from this direction, but this direction, vertical direction, has lower polarizability. Okay, so obviously it will give different Rx value, refractive indices value. Okay, in macroscopic you can say, suppose this is the molecule. Okay, so refractive index are different. N1 days is not equal to N2 days. So what is the difference between these two refractive indices is known as birefringence. Okay, so these are all the characteristic, optical characteristic you can say, of your polymer sample, which we have discussed here. Okay, so reflection and gloss. So what are the factors which affect the reflection and gloss? Are gloss increase with, okay, increase refractive index. Okay, obviously if refractive index is increasing, then more reflection is there and it will give more gloss. Increase angle of incidence. Okay, it will also give you more gloss. And gloss rough surface. Okay, I have already discussed, if surface is lost, then there will be light will be reflect in different angle. Okay, so it will not give you good gloss. So rough surface result in light scattering. Optical inhomogeneity, optical inhomogeneity just beneath the surface. Okay, if it is optical inhomogeneity, then also it will reduce gross. Sorry. Then other factor affecting growth: polymer surface morphology, processing parameter. Okay, so the surface phenomena is also depend on the polymer processing. Okay, what are the parameter which are being used while the processing of the polymer? Then mold finish. Okay, how your mold is good. Okay, how is its finishing? Okay, it is also depend on that. So the one example is given here. Just if you are going to add rubber, okay, so it will decrease the gloss. Okay, gloss of the sample decrease by adding rubber. Okay, so these are the things. Now I think you are able to understand the answer of this question. We have all discussed all the terms which are being asked in this question. Okay, so now we are going to move question number 4. So question number 4 is also very interesting, as we discussed in starting of the class, Fox equation and all. Okay, so a blend of polymer A and polymer B found to give 2 Tg. Okay, so this blend of polymer A and B giving 2 Tg, 140 degree and 112 degree. What can you conclude about the miscibility between two polymer? Okay, so I think it is very easy answer. If you understand the Fox expression, then also it is, because it is giving 2 Tg. Okay, so it is not completely miscible. Okay, so what is the condition for completely miscible polymer? That it will give only 1 Tg. Okay, if only single Tg. Okay, if single Tg is there, then you can say that your polymer, two polymers or blend of polymer is completely miscible. But here this blend is giving 2 Tg, so it is not completely miscible. Okay, so this option is incorrect. Okay, if it is complete. Okay, so now Tg for polymer A and polymer B is also given. It is 150 and 100 degree centigrade. Okay, so if it is completely immiscible, okay, if they both polymer are different in behavior and they do not like each other, so these are completely immiscible, then what is the phenomena? Then it will, then also it will give 2 Tg, but the Tg will not change. It will remain same. Okay, but this is not our case. In our case, Tg is also changing, so we can say no, it is, this option is also not correct. It is not completely immiscible. Okay, so we can compare Tg of pure polymer A and B and Tg of this blend. So these have little different. So this difference is due to some miscibility, or we can say partially miscible. Okay, so these polymer A and polymer B are partially miscible. So C is the right answer of this question. Okay, I think it is clear. Any doubt you can ask. Okay, so it is written here. This is the detailed solution. As the blend shows two Tg which are not same as the individual polymer, the polymer are partially miscible, which I have explained you. Okay, so now question number 5. Estimate the glass transition temperature in centigrade as per the Fox equation for the completely miscible blend of polymer A and polymer B. Okay, 70 degree. The Tg value of polymer A and polymer B are 45 degree centigrade and 75 degree centigrade respectively. Okay, so what values are given? I think weight percent is given. Okay, weight percent is given. So I think you need to convert in weight fraction. Okay, 0.03 and 0.07. Okay, so you can use here Fox equation, which we has already. Okay, Tg of this copolymer will be equal to W1 Tg1 plus W2 Tg2. Okay, so weight fraction is given zero point 0.3 and Tg1. So you need to convert it in Kelvin. So 273 plus 45. So it will be 8, 1. Okay, 318. So 0 0.3, then 318 plus W2. So it will be 0 0.7 divided by what happened? 0 0.7 divided by 75 will be here. So 7, so 7, 348. Okay, the value about 1 upon t. Okay, further if you calculate, then you will able to answer this question. Okay, whatever limit is there. Okay, by using Fox equation, you can solve this question. I think it is solved here also. Yes, it is already I have explained you. Okay, so see if what question is asking, estimate the glass transition in centigrade. So okay, so you need to find out in centigrade. If you will write answer in Kelvin, then it will be your answer will be right, but it will computer will consider it as a wrong. Okay, so please be careful about this type of question. Okay, so this is very good question. For a polymer sample, elastic behavior is demonstrated as. Okay, you have any polymer sample, elastic behavior. Okay, so we have discussed viscoelastic behavior of the polymer. Okay, viscoelastic behavior of the polymer. So our polymer can behave as a viscous liquid and same elastic like elastic also. Okay, but there is some condition. Okay, so we know that if shear stress, shear rate, okay, if shear rate is high, means shear rate means you are going to deform it. Okay, deformation rate. Okay, so if you are deforming it in very high rate, rate means time. Okay, so in short time, high rate means you are deforming in very short time. Okay, so if your shear rate is very high, then what will happen? Your polymer will not have sufficient time so that this chain can be flow or adjust or move. Okay, so that's why it will not the chains of polymer will not able to move in short time because your shear rate is very high. So it will behave as a so your polymer will behave as a elastic. Okay, so at high shear rate, high shear rate, first of all. Okay, if a shear rate is high, but if your temperature is also high, okay, so at high temperature, your chain will be able to move due to kinetic energy, and due to expansion they will have some kinetic energy, and due to expansion the chain will able to move, and all these phenomena will be happen. Okay, so this phenomena will considered as it will be move toward viscosity. Okay, or viscous behavior of polymer. So high temperature is also not required to behave your sample as a elastic. Okay. So other term is lower temperature. Okay. So if these two conditions are there where stress rate and lower temperature is applied, then polymer sample will behave as elastic behavior. Okay. So this will be the right answer. So C will be the right answer. Okay. Because higher shear rate and low temperature. Just opposite to that, lower shear rate and higher temperature will be responsible for viscous behavior of your sample. Okay, so lower shear rate and high. Okay, so this for viscous. Okay, it is for elastic. Okay, so these are the condition which required. Okay, for polymer means uh, polymer can show both property, elastic and viscous, but it depend on the condition. Okay, so what is the means processing condition, or how you are going to making, how you are going to applying stress, strain, shear stress, shear strain. Okay, so this is all about this question. If you have any doubt, you can ask about this question. If you have, I will solve just now. But if you have any other question or any doubt, you just write me. I will give you detailed answer. Okay. I have already shared you my mail information. Okay. So you just write me today. After this class, I will give you answer till morning, till Monday. Okay. So this is the detailed answer we have discussed. Okay. So high shear rate and low temperature polymer chain do not have enough mobility to move each other. Hence, elastic behavior is demonstrated. Next question is, which of the following property get improved over base polymer on addition of nanofillers? Okay, so it is given nanofillers. Okay, so uh, heat distortion temperature, yes, it will if you are adding nanofillers, it will improve heat distortion temperature. Okay, Barrier property also, okay, because it will get space in your polymer matrix, and it will also able to it will provide barrier property for the polymer. But ductility not, ductility will not improve, and transparency also not improve. Otherwise, however, it will be decreased transparency if you are adding if you are adding opaque nanofillers, then it will be transparency will be reduced. Okay, so either A and B both are the right answer. Okay, heat, distortion, temperature, and barrier property. So these are two right answer. Then question number 8, damping ability of polymer sample is measured by G1 storage modulus, G2 loss modulus. Okay, so 10 delta is G2 up G2 upon G1. Okay, so this is about the, yes. So damping ability, it is known as a damping ability. Okay, so see, these two G1 is storage modulus and it is related to elastic property, and G2 is loss modulus and it is related to viscous property. Okay, if G double dash is higher, okay, or loss modulus is higher, you can say that your polymer is behaving like viscous liquid. Or if G1 is higher, then your uh, polymer is showing elastic property. Okay, so this is the measure okay, of damping property. Okay, so if G double dash is higher, so your 10 delta will be higher, and it will be equal to your damping ability will be also increase. Okay, so this is all about this question. Okay, so D will be right answer. Okay, damping ability of polymer is measured by G double dash by G dash. Okay, so damping property. Okay, so what is the damping property? You should know about that also. Damping property refers to the ability of material to dissipate elastic strain energy. Okay, during mechanical vibration or wave propagation, whatever is there. Just a minute, what happened? Okay, so means damping means if damping property is higher, means your polymer is able to dissipate energy faster. Okay, why it is so? Because your polymer is showing viscous behavior where chains can be moved easily. Okay, so so it can dissipate or remove. Dissipate means remove. Okay, so it can dissipate elastic energy faster. Okay, if G double dash value is higher, if loss modulus is higher. Okay, so it will release its energy faster. Okay, if G dash value is higher, and by common sense we can understand that G dash is higher means your polymer is viscous, and because it is viscous, so polymer chain can adjust accordingly. Okay, and it can adjust whatever strain is applied on this polymer chain of your polymer material. Okay, so this is the detailed solution. For a viscoelastic material, the stress lags somewhat behind the strain. Okay, yes, we have discussed this thing. In viscoelastic, the stress lags some. Okay, so these are, I think you know about this graph. Okay, it is not like that. So it is lagging like that. Okay, okay. So this phenomena already we need to increase. Okay, these are the lagging. Okay, so suppose this is the uh, so stress lag. So suppose it is the strain. Okay, so this is the stress. Okay, so it is the lagging. So what question is asking here? So what is the explanation here? For a viscoelastic material, the stress lag somewhat behind the strain. Okay, This is considered as damping process. Increase in liquid like behavior. Liquid like means viscous behavior. Okay. So increase in liquid like behavior, the simultaneous decrease in elastic behavior. Okay, obviously viscoelastic. Okay, so when you increase okay, so your polymer can be behave as viscoelastic and can be behave as a, sorry, can be behave as a viscous or can be behave as a elastic, but it is depend on the condition. Okay, which we have already discussed, means high shear rate. If it is high shear rate and low temperature, it will behave as elastic. Okay, similarly, if it is high temperature, uh, if it is low strain rate, okay, and high temperature, it will be a very viscous. Okay, so in elastic behavior will produce more damping. Hence damping is measured by most appropriate by g double dash by g dash, loss modulus by storage modulus. Okay, now question number 5, question number 9. Brominated aromatic works as a fire retardant. Okay, so fire retardants are being used, okay, which can protect your polymer to get fire. Okay, so but brominated aromatic ring is how it's work. This question is asking how brominated aromatic works as a fire retardant. Okay, so it is forming an insulating charge node interfering with chemical reaction that maintain the fire, maintain the fire and promote the spread of flame. Yes, yeah, this is the right answer. Okay, interfering with the chemical reaction that maintain the fire and promote the spread of flames. Yes, then releasing water not. And okay, so B is the right answer of question number 9. Okay, so these are some uh, okay, so these are the brominated aromatic rings, BFR, are commonly used to prevent fire in electronics and electric equipment, which account for more than 50% of their application. Okay, sometimes it can be more than 50%. In addition, BFR are used to reduce the flammability of the plastic in many products, such as household article, furniture, mattress. Okay, and some examples of brominated aromatic rings are given here. Okay, which are bromophenols. Okay, bromo bisphenols. Okay, because two phenols rings are there, bromo bisphenols and bromophenols. Only one ring is there. So these are the some common bromophenols which are being used as a as a brominated aromatic ring. Okay. So question number 10. Question number 10 is identify the behavior of plastic sample presented in following plot. Okay. So this graph we have discussed in first question. Okay. So the topmost, which is I think you know about the Bingham plastic. Okay. So this is for Bingham plastic. Okay. It has already some. If you want to see, I will just. Yes. So this plot represent various type of material and their property. Okay. How it behave with the shear rate. Okay, how their shear stress relate with their shear rate. Okay, so according to that we can classify polymer in different type of plastics, which are caisson plastic, Bingham plastic, pseudo plastic. Okay, then dilatant or shear thinning, which shows shear thickening, sorry, not shear thinning, dilatant, which represent shear thickening, whereas pseudoplastic represent shear thinning. Okay, so these are the some type of plastic. So in this question, Bingham plastics is the right answer. Okay, so I have discussed this assignment question, okay, of the last semester, week 8. Okay, so I think it is clear from my side. If you have any doubt, you can ask. Or after 5 minutes, I will discuss some concepts because we have some time. Okay, so we will discuss some important concepts. Any doubt from your side? Any doubt from your side? Okay, so we will meet after 5 minutes. Okay, so just come back. I will be here at around 7. Okay. Hello, Manisha. Am I audible to you? Manisha, do you have any doubt?
Yes, yes, sir. Audible.
Yeah, yeah. Do you have any doubt regarding this assignment question or all?
Till yet, it is understandable because I am not go deeper into the reading materials.
Okay, so means you have to solve the assignment. I think there is some deadline, na? So have you solved or you will solve later?
For week 8,
Ha, week 8.
no, no, I am not solved yet.
Oh, yeah. So whenever you solve, if you have any problem, then just write me. Okay. Did you get my
Through when
sorry? Did you get my email ID?
in past hour,
Yeah.
I saw your mail ID
Ha ha.
in this session.
Ha. So you can write me on that email ID. Okay.
Okay, thank you.
Yeah. Okay. So now we will discuss some physical property. Okay, of the polymer. So thermomechanical property, I will go fast. Okay, some only I will give some outer flavor. If you need to understand deeper, then just tell me. I will make you understand. Okay. So this is a thermomechanical property means a thermally dependent mechanical property. You can say in detail, it is uh, thermally dependent mechanical property means how polymer mechanical property change with temperature in simple language. Okay, so polymer as we are using in our domestic uses also, we need to we need to worry about the temperature at what the appliance are being used. Okay, because sometime you will see that if you are using the polymer utensil or polymer sorry, polymer domestic appliance on higher temperature, these are getting melted or becoming softening. Okay, so why it is so? Because they have this polymer have some Tg, Tm like that. Okay, generally when you increase temperature and when it crossed Tg of this particular polymer, it will get deform. Okay, so it will make your appliance or your domestic utensil or domestic apparatus, whatever you are using, it will become damaged, okay, or non-usable due to uh, extensive use of means use of your material at higher temperature. Similarly, some plastics has Tg at lower temperature also. Okay, so sometime it will sometimes some bottle which are being kept in refrigerator. Okay, freezer of the refrigerator you can say. So when it cross its TG limit, lower limit, okay, so the plastic become brittle and it also damaged. So these are the properties of polymer which is depend on thermal condition. Okay, so here these two graphs I think you are able to see is representing amorphous and semi-crystalline polymers. So in amorphous, we can see here, just a minute. In amorphous, this blue graph is representing tensile strength. Okay, so tensile strength is being decreased. Okay, tensile strength is being decreased. Okay, as temperature is increasing. Okay, so it is decreasing at Tg, it is decreasing further, and sharply it is decreasing, you can see like that. Okay, and in the middle in the middle of this graph it is measured as Tg. Okay, and all, then it will become viscous liquid, so the tensile strength will be almost zero. Okay, similarly, this graph is representing elongation. Okay, so elongation is almost means it is not increasing, negligibly increasing, at lower Tg, but from the Tg it is increasing very high. Okay, you can see after Tg this elongation is very high. Okay, and this is for amorphous material. Similarly, in semi-crystalline polymer, initially because in semi-crystalline some part of polymer is crystalline. Okay, it is like that. Okay, so this is the semi-crystalline. Okay, why? Because it's contain both phase, viscous and crystalline nature. So when it is below Tg, it will be brittle. Okay, this polymer will be behave as a brittle. At Tg, okay, at Tg, some this blue curve is here also same for it is also about tensile strength. Okay, so at Tg, it will be decreased little bit due to amorphous region of this semicrystalline polymer. Then then it's tough, elastic, hard. Okay, because here in this region the crystalline part of this polymer uh, means due to temperature, as temperature is increasing. Okay, so so the tensile strength is decreasing because this crystalline part is getting delaminated, or it is getting it is becoming viscous, or we cannot say means the crystalline nature is being lost due to polymer. Okay, but at a certain Tm, okay, it near Tm, this tensile strength is decreasing faster. Okay, and after melting it is approach to zero. Similarly, elongation is also increased. At Tg it is little bit increased due to viscous behavior. Then elongation is increasing due to chain opening of this crystalline polymer, and the finally at just before the Tm it is highest at the peak, and then it is elongation is decreased. Okay, so we can say that this thermo the mechanical property of polymer is highly depend on temperature. Here also these two graphs represent the thermomechanical property. Okay, but it is based on molecular weight. Okay, just a minute. So this the first graph is represent for amorphous. Okay, so at a lower molecular weight, so up to here you can say molecular weight is increasing in this direction. So up to here at lower molecular weight, the rigid glassy solid. Okay, at Tg it is becoming viscous. Okay, liquid, mobile liquid. So just here at particular temperature, because molecular weight is very low. Okay, so rigid glossy solid molecular weight is slow means polymer contain very small chain. Okay, and as you increase the temperature, this polymer chain will start to flow very easily. Okay, so it will directly convert in mobile liquid at the lower molecular weight. But as molecular weight will be increased, suppose we are taking example at that point, okay, this molecular weight. So then it is the polymer chain is very much larger, and this polymer chain are entangled in okay among each other. So what will happen? That it will take time. At Tg, it will means it will start moving and all. Okay, so first of all, the glassy, rigid glassy solid will convert in rubbery. Suppose here, so we are measuring here. Okay, rubbery, and by further increasing temperature, it will convert in rubbery liquid. Then finally, it will convert in viscous liquid. Okay, so many means you are able to see that for higher molecular weight, many phases are there in between viscous liquid and a rigid glassite solid. Okay, so this is all about amorphous polymer. But here in semi-crystalline polymer also, you can say if it is crystalline solid, okay, then it will convert in mobile liquid at lower molecular weight, similar to amorphous. But if molecular weight is higher, it is rigid semi-crystalline solid. Okay, rigid semi-crystalline solid. So here also, suppose intermediate molecular weight, it will when it will be heated, it will convert in tough leathery solid, and then finally in viscous liquid. But if molecular weight is very high, then it will convert in tough leathery, then rubbery state, then rubbery liquid, and finally in viscous liquid. Okay, so these are the phenomena. If molecular weight is extremely high, then sometime it will be means only form a rubbery liquid, and it will not convert in viscous liquid and all. Okay, so these are the different phenomena which are being used. Okay, to understand the thermal mechanical property depend on temperature. Okay. This graph is represent. I'm talking about this graph. So this graph is represent modulus with temperature. Okay. So obviously, when it is glassy, okay, or solid, whenever anything is solid, it has high modulus. Okay. So here it is high modulus, but as we are increasing the temperature in this direction, as we are increasing the temperature, it will convert in leathery. Somewhere Tg will be here. Okay, so it will become leathery. By further increasing the temperature, it will become rubbery and finally viscous, and finally viscous liquid. Okay, so for liquid, modulus is almost zero. Okay, so it is approaching toward zero. So see, if it is this is for amorphous, but if it is crystalline, okay, so the long modulus will be decreased little bit here at Tg. Then because it is semi-crystalline, so modulus will be almost negligibly decreased. Okay, and at the Tm it will be decreased further. But if it is cross-linked temperature, cross-linked polymer, so if it is highly cross-linked, then there is no Tm. Okay, so it is so the Young modulus is not decreasing at the cross link at the Tm. Okay, it is because there is no Tm. Okay, so by increasing temperature also the modulus is not decreasing. Okay, so these are the some phenomena which can be understand, because semi-crystalline there are some viscous. So this property is represented by viscous portion of your polymer, and this property is represented by crystalline portion of your polymer. But if it is cross-linked, then there is not you can say uh, it is already cross-linked. So Tg, so amorphous region will be there. Okay, because it is not 100% crystalline cross-linked. So some region represent this Tg, and due to that the Young modulus will be decreased. But after that, uh, it do not have any Tm melting point. That's why this okay. So the phenomena which happened at melting point will be not there in close-linked polymer. Okay. This graph also represent how the uh, okay. So this graph we have already discussed. As molecular weight will be increased, okay. So means its Young modulus also will be increased like that. Okay, but here you can see cross link, but how much it is cross link? If it is lightly cross link, then amorphous region will be higher. So the phenomena which occur due to amorphous region will be there. Okay, to up to here, Young modulus will be decreased. But if it is highly cross link, then amorphous region will be decreased. Okay, so this the decrease in elastic modulus will be very small. Okay, because highly cross link. So cross link part is very high. compared to amorphous region. So that's why this phenomena will be it can be understood like that. Okay, so see, it is also similar only if we are increasing molecular weight and all. Yeah, so this is the very important point for discussion, viscoelastic property. Okay, and in assignment question also we discussed many in detail what is the viscoelasticity and how the polymer can behave as a viscous liquid and also as a elastic. Okay, so polymer have both elastic and viscous behavior depending on the time and temperature. Okay, time and temperature. If temperature is high, viscous. If temperature is low, elastic. Okay, so this type of behavior are represented by polymer. So we can understand the first of all the elastic. Okay, so to understand completely about the viscoelastic property, first of all we should know about the what is the property of elastic material and what is the property of viscous material. Okay, so then we can compare that how our polymer is behaving as a viscoelastic. So in ideally elastic polymer, elastic if you are means pulling something, okay, means you are applying load, okay. If you are pulling some elastic material, you are applying the load, and when you release it, it will again come to its original state. Okay, so some elastic which we are using for domestic use also you can correlate with that. Okay, so this is the elastic. Okay, so it is already if it is 100% elastic, it follow the Hooke's law. Okay, sigma is equal to elastic modulus into strain. Okay, so stress is proportional to strain. Okay, how much stress you are applying, your material will be strained in the that amount. Okay, and at the moment you are removing the stress, it will again come to its original position. Okay, so you can see in this graph that at this point a time is equal to, you can say time is equal to t1 and t is equal to t2. Okay, so time is equal to t1, you are applying the stress. Okay, so this blank square is representing shear stress, whereas this filled circle is representing strain. So first of all, we are talking about shear stress. So at t is equal to t1 time you applied stress like that. Okay, up to that, up to this point, you applied stress. Okay, because this axis is stress and this is the time axis, and here it is strain. Okay, so there are two y-axes. Okay, so you applied stress up to here, then from t1 to t2 you kept this stress constant. Okay, and at t2 you remove this stress. Okay, and again stress is 0 here. At this point stress is 0, again this point stress is 0. Okay, and in between t1 and t2 you applied stress. Now if you see the strain, the moment you applied stress, strain is also increased parallelly. Okay, means at the same time instantly as you applied stress, strain is also increased up to here. Okay, you kept this stress from T1 to T2, so this strain is also remain same. Okay, from T1 to T2 same strain will be there, and as you remove this strain is also removed with the stress. Okay, so here also at this point stress is also 0 and strain is also 0. Okay, but at the t1 as you applied stress, strain is also at the full maximum value. Okay, and when stress is 0, strain is also 0, and when stress is highest, strain is also highest. Okay, so means it is following the same path. Okay, no lagging is there. Okay, so in same phase you can say stress and strain is same phase for the elastic material. Okay, so we understood about the elastic material. Now we are going to discuss about the viscous material, how viscous will be viscous material stress and strain will be behave with the time. Okay. Yes. So this graph is represent about the ideal viscous liquid. Okay. So when you are applying the load on the viscous liquid, it is not this graph is not in between stress and strain. Is strain rate. Okay. And this stress is proportional to strain rate delta explain okay, so this is the just a minute. Sigma is equal to eta, it is viscosity upon delta explained upon delta T. Okay, so it is a Newtonian flow. So at time again it is equal to time is equal to T1 and time is equal to T2. Here you applied stress, okay, up to its maximum limit. Then you kept constant for some time. Then again you release. Okay, so this is about the stress. Okay, this square, this square representing about the stress, but at the T1 this strain is not approached to its highest limit, it is gradually increasing like that. Okay, and up to here when you remove this stress, although the strain is remain constant. Okay, so you means you deform this your liquid and now it is deformation will be there. Okay, it will be remain in your liquid, in your viscous liquid. Okay, so means it is not removing. When you are removing the stress, strain will be remain there. Okay, so strain is remaining there, but in our elastic behavior strain is sharply decreasing with the stress. Okay, so this is the two graph. Okay, so we can say for strain, if only for strain if I am drawing, so it is for elastic behavior and it is for let me draw in different color. Okay, so so we can say this is for elastic and this is for viscous, viscous liquid. Okay, so this and with respect to time. Okay, so these two graph representing strain curve of viscous and elastic region. Okay, so if our okay, so how polymer graph should be look like? Okay, so because it is showing both viscous and elastic behavior, so first of all it will be straight. Okay, so it will be so like elastic behavior. Then because it is okay from here to here, because for elastic it is linear, but so it was constant, but for viscous it is increasing. Okay, linear graph linearly increasing. So it will be look like that. Okay, then it is decreasing here. Okay, so again it is decreasing, so we can draw like it is showing elastic behavior. Then for viscous it will be constant, so it will be like okay. So this is the curve for viscoelastic material, means it is showing if we are merging these two curve of elastic and viscous behavior, then we are getting the curve which representing viscoelastic behavior of polymer. Okay, so from how uh, this curve is plotted, which is also explained in upcoming slide, so you can correlate. Okay, why it is so, how it is done. Okay, I think it is clear. Okay, so this type of curve you will be able to see in next upcoming slide. Yeah. So I think you are able to see. Okay, so this curve I has already drawn in the last slide. Okay, so this property is elastic. Then this is the you can say viscous property. Then here again sharp drop, so it is elastic property. Then again it will be like that, so it is viscous property. Okay, load applied here and load released here. So this is the plot for viscoelastic material. Okay, is it clear? This graph is clear, I think. Okay. So again, these parameters are given at lower temperature, high strain rate, polymer demonstrate elastic behavior. Why? Because at lower temperature, polymer chain will not able to move. Okay. Similarly, at high strain rate also, deformation will be very fast. So that's why your polymer will behave as a elastic behavior. But at high temperature, where polymer will be expand, there is enough kinetic energy that polymer chain can be moved. And similarly, at low strain rate also polymer will have enough time to polymer chain can move. Okay, so it will behave viscous behavior. Okay, so it is depend how much high temperature and how much low strain rate. Okay, so but at moderate, in between these two things, it will behave as viscoelastic behavior. Okay, so again it is the curve between elastic modulus, temperature, log elastic modulus and temperature. Okay, so here you can see that from A to B, deformation, or you can say strain, is almost constant. Okay, but from B to C, from here to here, sorry, from B to C, where the glass transition temperatures occur. Okay, so due to glass transition temperature, the strain will be higher. Okay, like that. From CDE, from polymer is changed from leathery to rubbery and from rubbery to viscous, strain is very high, almost it is linear. Then then it is constant. Okay, because it is now it is viscous. Okay, so it is viscous. So from here to here, we are moving from elastic to viscous. Okay, so here it is elastic, it will show elastic behavior. Okay, and here it is so viscous behavior. Up to here, any doubt, Manisha? Any doubt? Okay, so this graph represent stress or strain. Okay, but it representing at how the stress strain curve depend on increasing temperature, similarly on increasing strain rate. Okay, so we have already discussed that age. First of all, we will discuss about the skinning rate. Sorry, increasing strain rate. Okay, so when we increase strain rate, okay, polymer will do not have sufficient time so that polymer chain can be arranged, so it will behave as a elastic. Okay, so we know how what is the stress strain curve for elastic. Okay, it is look like that. Okay, elastic means as you remove the stress, again it will come strain, so it is proportional. Okay, stress and strain is general proportional, and this curve is representing elastic behavior. Similarly, yes. Now, if you are increasing temperature, just opposite. Okay. So, as you increasing temperature, the polymer will have sufficient energy as well as it will expand and all. So, chain can be moved easily. So, uh, it will behave viscous. Okay, viscous property. So that's why its elastic modulus will be decrease. Okay, and by applying little stress, the strain will be higher. Okay, so this property is related to viscous property. Okay, so fast, low, and brittle. If strain rate is fast, temperature is low, it will form brittle rigid. However, if strain rate is slow, temperature is high, then it will a tough or ductile nature will be represent. Okay. Similarly, how its strain rate will be depend on temperature is represented here. Okay, similar concepts again and again coming. So we can measure this creep and stress relaxation. Okay, either by first, if we are keeping strain constant, then we can measure stress with time, or we can make constant, stress constant, and then we can measure strain with time. Okay, so these are the some concepts which I taught here. Okay, so I am waiting for you for more 5 to 10 minutes. Okay, any doubt or any clarification you need from my side, I will be here. Okay, any doubt, because I cannot explain all 5 lectures. Okay, however, if you have any doubt, you can ask me.